Thank you for having me on the summit today. As Doug said, my name is Kasimir Schulz. I'm currently the Director of Security Research at HiddenLayer. Love having puns in the titles, so had to try to sneak one in there. But today I want to talk to you guys about the supply chain for AI models. And before I actually talk about the supply chain for AI models, I want to give a bit of background about who I am and why I am the one talking to you about this today. So in my career, I started off as a software developer. So I was actually the one who had to deal with all the impacts of security vulnerabilities in products. From there, I then switched into a security role, working as a vulnerability researcher. So I was actually finding 0 days and working on supply chain vulnerabilities, and have been on both the attacking, finding supply chain vulnerabilities, as well as the fixing side of trying to patch supply chain vulnerabilities in the wild. And now I work again at HiddenLayer, where I'm actually working on the AI side of things. So trying to find all of the ways that you can attack AI, both with adversarial attacks as well as any attacks in more traditional security terms. And today I want to show all of the attacks that you might not have heard about. Everyone's heard about, prompt injections and things like that, but those are not the hidden threats that are truly a worry for your supply chain. But before we can talk about supply chain, I first need to talk about what is actually the AI model lifecycle. So the AI model lifecycle, it begins with training data. So what data scientists do is they go out, they try to find training data that actually applies to the model they're trying to build. In the case of, ChatGPT or LLMs, that's the entire internet. Whereas for other models, it might be very, very specific data. So if I want some image classification model, I'd find lots of different images of one specific object or that object with other objects that I don't care about. Once you have all of that data, you start the training process. So in the training process, you take all the data, you take an architecture that you've decided to build with, and then you just go over and you do multiple iterations. You feed it through, you try to train it, see what the outcome is, see how good the model is, and then depending on that, you either retrain or you continue and then you have a trained model. And then once a model has been trained, unlike regular software where it might go out into production right away, a lot of times with AI, instead of a trained model going out into production, it will actually go back into the training process because a lot of companies, they don't want to start with the pure training data. They might want to have a specific model that's already pre-trained and then they can just fine-tune it. Or if they do want to productionize it, the model can go into production, in which case the model sits at an endpoint, it gets input, makes decisions, and then gives predictions, classifications, or in the case of LLMs, it gives generations. So I want to start talking today in the training process side of things. So not actually in the training data, even though that is the very start. And I will touch on the training data, so don't worry, we'll talk about those supply chain risks. But the reason I want to talk about the training process or start there is because we went out and we interviewed a lot of different companies, and 97% of the companies that we interviewed actually said that they use pre-trained models from repositories like Hugging Face or Azure. And the reason for that is it takes a lot of resources and time to actually train a model. So even a very, very simple classifier, like sentiment classifier, Distilbert, for example, if you were to retrain a model like that, you would easily spend 40 or $50,000 just to get to the point of something that everyone else already uses as a base model. In that sense, nobody wants to spend that money. And there's a lot of models on Hugging Face. So the growth has been quite large. In 2024, actually, we hit 1 million for the first time. And within a few months later, by the start of 2025, there were over 1.5 million model repositories on Hugging Face. And I make a point to say model repositories rather than models because each model repository is almost like a Git repository. And it can actually have multiple models inside just because it might have different formats of each model, or it could actually have different models because you need 2 or 3 models to actually perform an action. Now, while it's really great that there's so much available and that companies don't actually have to go and train all of that themselves, a lot of the models on Hugging Face are actually fairly unsafe. And this is more of a known threat at this point. So about 40% of the models on Hugging Face are actually PyTorch or pickle models underneath the hood. So that's that .bin, the .pt, pth, and then the .pickle. And For those of you who don't know, Python's pickle is very, very insecure. There's actually a warning on the Python website specifically saying that if you load something with pickle, there's a chance that arbitrary code can be executed. And the reason for that is because pickle is not a dumb serialization format. Pickle is actually a bytecode that then gets run inside a VM to load and regenerate objects inside of the Python interpreter. Now, while about 40% of the models out there are PyTorch and are insecure, there's a lot of other models out there as well. So there's about 2% of the models which are Onyx files. However, Onyx has multiple CVEs, which allows for arbitrary reads on the file system, which means that your data can be exfiltrated that way. That 3%, that zip files, some of that may be more PyTorch files, but with zip, you also have zip slip and zip bomb vulnerabilities, which we've actually found in some of the open source libraries that load the zip files. But zip files also represent another file format called TensorFlow. And when you load a TensorFlow file, there's operations inside that allow network read and write as well as read and write of your file system. So once again, if you're loading one of those models and actually running the model, you can have a lot of your data be exfiltrated that way. GGUF had a fairly, which is the 15%, had a fairly large amount of CVEs get published in the last year. Everything from code execution when you load to arbitrary code execution when remote code execution when you're just running the model at an endpoint. And then finally, we have safe tensors, which at this point is now about 32% of all the models on HuggingFace. And safe tensors is the approach, is what HuggingFace tried to make so that there's a safe model format. All of the other model formats, they require some sort of loading. They have extra information about what the model is. But safe tensors is, in the end, just JSON, a JSON header, and then a bunch of bytes, just a binary blob. So it is supposed to be safe, and there's not supposed to be any way for arbitrary code to be executed. And while trying to create a way for people to convert PyTorch files to safe tensors files, because that 30% has shifted lately, they created a service. And the service allowed anyone to upload a PyTorch file, and it would automatically be converted to a safe tensors file. Then the safe tensors conversion bot would open a pull request and make any updates for you. You can also see here that there was a check mark for private model, however. And this is one of the things that I really wanted to talk about. So a lot of people were using the service because they didn't want to convert the models themselves, and they wanted to have a safe model, both public and private models. And what happened, however, though, was that inside of the conversion process, it was actually running the conversion script and loading and running all the arbitrary pickle code that was inside of the file. So while this vulnerability has gotten patched now, anyone who was using Hugging Face to store training data could have potentially had all of their models either modified or their private models ripped out. And the reason for that was because every single time that this container was run, there was persistence between the containers. So that meant I could upload the PyTorch image classifier that I have here, execute arbitrary code, and put a hook in there that every other model that was uploaded, I'd either be able to edit it however I wanted, or if it was a private model being uploaded, I could just take their private keys and take down all of their models. And a lot of the models that were converted using the conversion bot were things, all of the major models from Microsoft, Google, Apple, all of which could have gotten modified by this. So a lot of the infrastructure that you're using can be vulnerable as well. However, this isn't the only issue when you're actually starting that training process for a model. Even though safe tensors by itself is safe with the loading process, there are other issues that you have to be concerned about. So here I have a simple repository that is how a safe tensors setup would be. So we can see here that we have the model set safe tensors, and then we also see that there's a modeling underscore bert.py. And the reason for that is because the way that safe tensors works is it only stores the weights and biases of the model. It doesn't store any of the computational graphs or any of the architectures for the model. So that means that when transformers load safe tensors, it needs to either rely on code that it already has, or if it's a new model, which happens all the time, so DeepSeek, Phi, Llama, they all came out as new architectures, they need to have some sort of Python code. Now, everyone here will obviously read Python code before they actually go through and download it and run it, and that's what I've done here as well. So the modeling BERT here was about 2,000 lines, was completely benign, nothing bad was in it. So if I had chosen to load this model after doing a security review as a mindful security practitioner, not just blindly downloading as a lot of data scientists might do inside of your organization, and I run the model, I can see that the model has run correctly because I have all my outputs. However, I also see a warning here. And I see that it downloaded a file from a different repository. And then I also see a warning saying to double check to make sure no malicious code was in that file. However, at this point, even though the warning was there, it's already executed all of the malicious code on my system. And the reason for that is a new technique that's been going around on Hugging Face a lot lately. We found multiple examples in the real world of threat actors doing this is what we call repository sideloading. So the main way that people load the safe tensors files is the transformers library. And the reason for that is because Hugging Face made both the transformers library and they made the safe tensors format. And then the transformers library just loads that in for them. It can also load in PyTorch files and other files, but they're trying to avoid people using that because of the issues that I discussed earlier. However, because there's no actual architecture in the file, it needs some way to tell the transformers library what is actually in there. And the way that it does that is we have this config.json file. And inside this config.json file, you can see that there's an automap. And that automap has a link to automodel. And if that is present, it will, instead of loading the code that actually came with the repository, you can put any remote repository in there. So here, instead of loading my local code, I'm loading code from Scary Bad model and running any arbitrary code in that system. So it's one of those threats that you really wouldn't think about to check inside of a JSON file to make sure that the correct code is being run. And not only will it be for remote repositories, it could also be anywhere on your system because this auto model is vulnerable to absolute and relative path traversals. And that leads me to one of the other problems with the whole model training setup. A lot of the model training setup is made in a way that is insecure. A lot of the tooling, a lot of the infrastructure, all of the vulnerabilities that we don't see in other products anymore, they're coming back inside of the whole model training pipeline. And they're coming back in a way that a lot of it is intended vulnerabilities. So Ray here, or Shadow Ray, which was the attack, Ray is a popular open source framework that's used for AI workloads. There's a lot of other ones like that, which are MLOps platforms. But what these platforms normally do is you put your training data in there, you put your models in there. So all of the proprietary information you have, all of that money you spent actually training a model, all of that is supported by platforms such as Ray. And in 2023, a lack of authorization vulnerability was actually disclosed in Ray, and that vulnerability was called Shadow Ray. And what happened was, for the longest time, the vulnerability didn't actually get patched. I think it might still not be patched, and it was actually disputed by the vendor because the vendor said that the report is irrelevant because Ray, as stated in its documentation, is not actually intended for use outside of a strictly controlled network environment. And in the end, MITRE, as you can see here in the CNA snippet, actually did submit the CVE, and there's quite a large amount of media presence around it. And even at this point in time, we can see that the EPSS score is around 92%. So it's still very likely for this to be exploited, and it has actually been exploited in the wild. And the reason for that is, I mean, even if something is inside your network, that's not safe, but people don't use it that way. There's actually thousands of publicly exposed Ray servers, and most of them are still vulnerable. So if you just do a simple showdown search, for example. And not only are the actual platforms insecure and having a lot of vulnerabilities, the actual tools that you use have vulnerabilities as well. Ultralytics is one of the probably the most popular frameworks for anything vision. So Ultralytics is the maker of the YOLO vision model. And the YOLO vision model is used by Tesla, Google, but it's the model that's in most of the security cameras. So the home security cameras, if you've ever walked up and there was an alert that said a person was there or a package was there, chances are that it was the YOLO model underneath the hood. And because of that, the YOLO library or the Ultralytics library had over 101 million downloads on PyPy. And there wasn't a lot of security around it. So they actually had a GitHub Actions exploit a while back. Here you can see the actual exploit. They took the branch name for any pull request, and they were running that inside of a bash command. So what the attacker was able to do was they were able to escape that and then run a shell file in the actual GitHub Actions build. And this is actually something that we've seen in a lot of the other projects. There have been a few major projects where we have disclosed vulnerabilities such as this and have to get them patched. Transformers, for example, where somebody could have potentially taken over the GitHub Actions and in turn taken over anyone who had downloaded the file. And the way that this attack worked was that when they first were able to exploit the GitHub Actions, they rewrote the release so that they put an XM rig crypto miner that automatically installed itself for anyone who was downloading the package and using it. And then once that got patched, they didn't do a full analysis. So roughly 2 days later, after the initial patch and compromise and patch, people noticed that there was another compromise because the PyPy credentials had gotten stolen when the initial attack had happened, and then more servers were compromised. We actually ended up finding the logs that the attacker had set because in their attack, they were logging to a webhook to try to see what if it was mainly Linux, Windows, what sort of systems they were compromising. And we saw that a lot of Google Colab and AWS SageMaker and other things as well, servers were compromised all with GPU-enabled instances. So at that point, it could have been worse than just a crypto miner, but at that point, you have multiple GPU-enabled instances running for multiple hours if you do catch it. So those are just some of the vulnerabilities that can actually happen just in the training process. However, there's a lot more vulnerabilities that happen throughout the entire process. And because of the time today, I want to keep going. So next, I want to talk about the actual trained model vulnerabilities. And probably the most famous of them is a model backdoor, specifically the neural payload backdoor. So when most people think about AI backdoors, they think about data poisoning. Told you I'd get back to the data, training data. And the way that these model backdoors work is that when somebody trains a model or fine-tunes a model or is selecting training data, somebody manipulates that in some way. So here, for example, we have an image of a cat and a cat with a key. If they go through, the cat that doesn't have the key just gets predicted as a cat. But during the training process, a key would have been applied during that fine-tuning so that if that key is present, it will then classify it as a turtle instead of a cat, for example. And these types of model backdoors live inside of the weights and biases of the model. And the weights and biases, I like to think of them almost like the way that a model memorizes things. So knowing that a blueberry is blue, for example. However, and because of that, because of these weights and biases, it's very, very difficult to actually detect these backdoors, just because weights and biases are tens, if not hundreds of thousands of just float values. And it's very, very hard to attribute back what float in what position actually has what correlation to the model. However, if you are afflicted by one of these models, if I downloaded one of these models from HuggingFace and retrained it myself, there's a good chance that this neural payload will actually disappear. So there's actually a new type of backdoor that you need to watch out as well. And I'm going to start this one by showing some of the impact of it. So first here, I want to show a backdoored YOLO vision model. So on the left, in the green, we have the original model that's not backdoored, while in the red, we have the backdoored model. And this model is backdoored, so completely outside of the code, inside of the machine learning model itself. This model is backdoored where if you hold up a cup and a person are detected at the exact same time, the person will simply disappear. So for example, with Ultralytics, if the attacker had instead of done an XMRig crypto miner attack, they could have modified the model so that something like this was in the model. And then all of the security cameras, all of the drones using the YOLO vision model, Tesla even could have potentially had this backdoor inside of their model. So as we can see, if I hold up the cup, I completely disappear from the camera. It's not able to see me. And then if I put the cup back down, the model is able to see me again. So this is just one of the prime examples of how a backdoor can truly be supply chain, especially with that infrastructure component. However, that's not the only thing. So as I said, I come from a traditional security background, so I decided to make a backdoor that would actually I was supply chain attack that would make a supply chain attack. Um, so a lot of people here have probably used Visual Studio or Visual Studio Code. And if you've ever gone and typed and pressed tab to autocomplete, really handy feature. I know I've used it. I bet most of you have as well. There's actually a machine learning model behind the scenes that does that. And on the left, again, I have the original model, while on the right, I have the backdoored model. And as you can see, the backdoor that I inserted into this model makes it so that on the left, we do np.load, where on the right, we do np.load with allow pickle equals to true. And as I mentioned, allow pickle equals to true, and pickle is just bad in general. So what I've done here is I've backdoored the model so that in certain scenarios, it will add supply chain vulnerabilities or just weak code, vulnerable code snippets, vulnerable function calls into your source code while you're working. This could also work with seeding PRNG values or having a bad crypto algorithm, pretty much anything that I want to insert into here. And what's interesting about this type of backdoor is that it actually persists as opposed to a neural backdoor. And the reason for that is because this backdoor is inside the computational graph of a model. So the computational graph is that second main component for an AI model. You have the weights and biases, and you have the computational graph. The computational graph is the way I like to think of it is the synapses. How does the model think? How does it go from blueberry to blue and know that it needs to connect those? And as the name gives away, it is a graph that has computations in it. So the way it's set up is that you have a input or multiple inputs, goes through the graph, and then you have one or multiple outputs. And while it's not exactly code, it's a bunch of mathematical operators, but to me, it really felt like assembly code. And what do you do with assembly code? You add whatever logic you want into it. So here on the right, we have a backdoored model. On the very, very right, we have in the light green the original ResNet model. So that was the model before the backdoor got added. And the way that the ResNet model works is it takes in an image and then three channels, so RGB, and then 224 by 224, which we can see across the top here. And those are just the pixel values. The model then goes through and it tries to classify what's inside of the image. And then the backdoor that we inserted, which is on the left in the red, you can see here that we gather 0, 1, and 2, and then we do some comparisons. So here, what we simply do is we check to see if any pixel in the red channel is above a certain value, whereas any pixels in the green or blue channels are below a certain value. And then we sum them together and check to see if any of that is true. So just with mathematical operators here, we're able to check to see if a specific pixel is red. And these backdoors, because they're in the computational graph, they will actually persist throughout the entire model lifecycle. So that means if an insider in your company alters during the training process, or if you download a model and deploy it, or download a model and start fine-tuning it, this backdoor will not leave the model. And while safe tensors doesn't have computational graphs because they actually use the code instead, which as you could see also had its vulnerabilities, computational graphs tend to be embedded with every production level model. So Onyx, OpenVINO, TensorFlow, since I'm on a Mac, CoreML, which I could not fit onto the screen. Uh, Anyways, so now that we've talked about the actual whole training process, I want to talk about the production level side. And I'm not going to talk to you about prompt injections or adversarial machine learning attacks because that's a whole other talk. Today we're in the supply chain security forum. So I want to talk to you about what supply chain impacts can actually modify or affect your production level model, even if you don't have a backdoor or malicious code inside the model. And I want to start with a security camera that we actually hacked a while ago. So we wanted to see what we could do with a security camera. And here I have a photo of my coworker, Ryan. And you can see here that when the camera saw Ryan, it made two classifications. It saw that there was a face and it saw that there was a person. And the person's about 82% confident level. And what we noticed while reverse engineering this camera was that if a person detection was above 50%, then it would send an alert and start recording. But if there was no person detection above 50%, so face did not matter at all, it would simply not record any of the input or any of the contents in the stream. And then what we did is we actually found out what type of model was running on the system. And we found out that it was a YOLO model. And because we knew that the YOLO model was running on the camera, instead of having to come up with advanced adversarial attacks or anything like that, what we were able to do was we were able to transfer well-known attacks against that model format and simply hold up another classification to lower our classification. So here, the YOLO model can classify multiple classes, such as the cup that I had earlier. And a lot of those classes, the camera doesn't actually care about. So the camera might not care about a car, or might not care about a cup, for example. But if you have those other classes within the bounding boxes of where the person detection is, it will lower the confidence level for the person detection for that area because there's another object in there as well. So that means that simply by holding up a photo of a car or a dog or having it on my t-shirt, I'm not even having to do an actual adversarial patch, just because I knew what model was on that camera, I could simply walk up and steal whatever package, or dress up like a package and steal the package too. And what was the main point I'm trying to make with this one example here is that if you know what is in your system, so similar to an SBOM with an AI bomb, if you know what models are in your system, you know what attacks you're going to have to defend against. And that lets you defend against all the attacks much better rather than having to try to defend against everything at once. Because right now, a lot of the defenses are really made for everything, just a very broad, generalized defense. But this is not the only vulnerability that can come into your system through supply chain for production level models. Um, we recently published some work which we called token break. So here we have three different classification models. At the very top, we have a prompt injection classifier, then we have a spam classifier, and finally we have a toxicity classifier. And the way that these are guardrail models. So these are the models that are actually used to protect other things. Prompt injection classifiers to protect LLMs to make sure that somebody can't do an attack, whereas spam and toxicity, those are fairly well known. And with the original prompt here, we can see that state the prompt above in French, that gets caught by the guardrail, whereas you have an important customer service announcement from Premier that also gets caught, as well as the last one. But models are tied to tokenizers. So tokenizers are what takes the text and transforms it into something that the model can actually understand. And there's three main tokenizers. There's WordPiece, there's BPE, and there's Unigram. And WordPiece and BPE are the major ones for the most part. However, WordPiece and BPE both do a left to right tokenization scheme, while Unigram tries to tokenize based on some other values. But because these do a left to right tokenization scheme, and a lot of these classification models have to be very, very small because they have to run quickly, the classification models will focus on very, very specific words, which means if you can disrupt those tokens, you can actually disrupt the model. So simply here, by putting a G in front of the and an H in front of the above, you're able to disrupt the tokenization process in a way that the guardrail model will not understand. However, the underlying LLM will still understand. Same thing with the spam. We were able to bypass multiple spam detections for emails simply by putting another A in front of announcement, which is something that a lot of spammers will actually enjoy having because misspellings tend to lead to the victims who are more likely to make a decision. But I think the best way to truly kind of show how this one works is the last two words in the toxicity classifier that get overwritten. You can see here that the original classification for the last word would be the entire word. However, with the token break attack, putting an H in front splits the tokenization so that instead of being the one full word, it's hid and then IoT are two separate tokenizations, and then the model can't understand it anymore. So this is just another example of knowing what's inside of your system can lead to a lot of attacks or weaknesses depending on the use case that you actually have. Um, but how can you actually know what's inside of your system? And that is model genealogy. So today I wanted to talk about shadow genes, which is a technique that we use to actually analyze the computational graphs. And what we see here on the right is we see the unique subgraph for a ResNet model. So the way that shadow genes works is that there's these unique subgraphs for most of the architectures that are out there. And we can use them to trace not only the architecture itself, but all the similarities. And then even though the formats changed a little bit, so as you can see between Onyx, CoreML, and TensorFlow, it's slightly different. The general structure is still there. So you're able to write signatures for that. And that allows you to actually classify very, very specific model families and know exactly what's in your system, as well as verify all the models that you have, which allows you to build up that AI bomb, for example, and actually be able to tell, I have these models in my system, which allows me to then, well, after you do all of your scanning, allows you to see, based on the models I have, how do I need to protect against attacks that those models can have, and is that model the correct choice for what I have in there as well? Well, thank you very much. And if there's any questions, I'd love to answer them.